This tool is very useful. I mean, if you want to simulate really a maneuver, I will not go and do it Dorsal. I'll just do the UVLM. If I'm doing stability analysis and error elasticity, I'll do the state space model. It's very useful, very practical. If I'm doing just simulation for a maneuver, I will do the UVLM because it's more accurate than the state space model. It allows for wake deformation. The wake at the end of the day will be freely deforming like here. Okay? And like I said, we are not imposing the singularities on the x-axis like we did in the analytical case, because we're not looking for analytical results. Rather, we distributed the singularities over the actual shape, okay? So you can account for flexible airfoil and all that. The applications are immense. You can use it to see how fishtail propel itself, right? How flapping lift themselves and all of that. So let's do a flow chart. Let's do it here. So we'll do geometry. So I'll say that this is meshing. So the meshing will give you what? You should prepare for me x, y of the bound vortices, the quarter chord, right? X, y of the control points, the 3 quarter chords of all panels. The normal vector of all panels. Okay? Yes, Anshul?
In your meshing, when you superimpose the panels, how do you account for the change in the camber? Like with the slope?
Yeah, this is a very good question. So I'll come to it in a minute. So then we can go now and start the simulation. Start time simulation. Time. So if you have the meshing, we can calculate what we call influence coefficient matrix. The matrix A this is what we call influence coefficient matrix. Matrix A that we constructed above. Because you have, look at this. What does matrix A? Here is Aij. Well, it just needs xy bound and xy control point and the normal. If you have these, so it's pure geometry. You have these, and if they are fixed, so if you don't have flexibility, actually you can do it offline, outside of the simulation loop. Because if it's rigid, it's even a camber line, but it's rigid, it will not change. You're just doing pitching, plunging, and moving back and forth as a rigid surface. So rigid surface, by definition, the distances between points are fixed, right? So these guys just come out of your mesh, and if they are fixed, you can even do this outside. So this can be done offline. By offline, I mean before the time simulation. So because it's time consuming if you construct the matrix each time step. Offline, if rigid. Once you have your matrix, at the end of the day, you're going to solve a linear system. So A times gamma equal right hand side. Construct A, construct right hand side, and solve. So the next step is to construct the right hand side. Do you remember the right hand side has how many pieces? How many pieces in the right hand side? Do you remember? How many major pieces? Motion, very good. And what else? And wake effects, very good. So the motion is given, so get me your kinematics or motion plus wake effects. So the wake effects here, you can see that we're going to call the Biot-Savart law in wake times, right? We have A, we have the right hand side, solve the linear system A times gamma bound equal right hand side. To get gammas. Once you get gammas, we're done. The rest is post-processing. If you want to get the velocity at any point, that's okay. If you want to get the loads, so velocity field, if you want, but more importantly to us as aerodynamics people, we like to see the aerodynamic loads, so pressure distribution, which we have an equation for it above. Get the loads, pressure distribution, get lift, drag, everything. Not drag, lift and pitching moment. And then don't forget to convect your wake. This is very important. So wake convection. Some people call it wake roll up. So here we update XY wake, right? We increase the number of wake by 1, right? And then we're done. So this is the time loop, okay? Okay, we'll start the program today and we'll finish it next time. Do you have any question, please? Yes, please.
There's basically CFD.
No, see, I mean, if you want to say CFD, it stands for computational fluid dynamics, right? So from this definition, yes, it's computational fluid dynamics. But the convention, the norm is to, I mean, this is too trivial to be called CFD. I'll say this is the numerical methods applied to fluid mechanics, aerodynamics, but it's not. CFD, if you're solving at least the Euler equation, I would say, okay, CFD. Euler, Navier-Stokes. If we're solving this potential fluid, this Laplace square phi equals 0. Yes, we can solve Laplace square phi equals 0 by CFD methods, like finite difference methods. Yeah, sometimes we do that. If you're taking a CFD course, this is one of the first examples that you do. But this is not even solving Laplace square phi equals 0 subject to boundary conditions by finite difference or finite element modeling. This is not like this. This is the discrete vortex methods. Okay. So anyway, so I will not call it CFD, although the definition applies. So let's see. Let's start here together. And let's do it together. Let's build the BIOS of R, but you have to engage. Okay, I'll not program it for myself. I have this program already. Okay, so you have to engage. You have to tell me what to do. So let's start with the BIOS of R. So we have a function, right? U induced is equal to BIOS of R. And you can look at your notes if you like. So BIOS of R takes what? Wow, it's here. Maybe, okay. So it takes xy point, right? Xy vortex. Yeah, he knows that the function BIOS of R. Anyway. So xy point is 2 coordinates of the point, xy vortex is 2 coordinates of the vortex, so we're gonna do the delta x, right? So delta x is xy vortex of the first coordinates of 1 minus xy point of 1 also. Okay, right? This delta x, and then delta y of the 2 coordinates, this is of 2. Then r squared, which I call r2, is dx squared plus dy squared. Right? And then the induced velocity is what? Induced velocity is what?
1 over 2 pi r squared.
Gamma over 2 pi r, but we do it for a single gamma, so 1 over 2 by r squared times two components. We said the two components will be the negative dy and dx, right? So we're done. It's super simple. So I'll do. Okay, I'll actually override mine.